Every time you start your car, you're not just turning a key, you're activating a chain of events that began millions of years ago. The fuel inside your tank was once alive, tiny organisms drifting in ancient oceans, long before humans ever existed. And today, that same energy powers cities, highways, and entire economies. But here's the real question. How does a thick, black, toxic liquid become one of the most refined and powerful fuels on Earth? This is the story of gasoline. Between 100 and 300 million years ago, Earth looked very different. Vast oceans covered much of the planet. Within these oceans lived microscopic organisms, plankton, algae, and tiny marine creatures. When these organisms died, they sank slowly to the ocean floor, forming a rich organic layer. Layer upon layer, they were buried under accumulating sediment, sand, and mud over millennia. Over millions of years, intense heat and immense pressure transformed these buried remains. This process created something entirely new: crude oil, a dense, energy-rich liquid, formed slowly, silently, deep beneath the Earth's surface. Every drop is the result of millions of years. But finding oil is only the beginning. To reach it, engineers must drill kilometers beneath the Earth's surface. Sometimes this means going deep under the ocean floor. Massive drilling rigs operate day and night, often in extreme conditions. When they strike oil, natural pressure may push it upward, but often powerful pumps are needed to bring it to the surface. This is not just engineering, it's a constant battle against nature. Raw crude oil is nearly useless on its own. To unlock its true potential, it must enter one of the most complex industrial systems ever built, the refinery. At night, refineries glow like cities of fire, filled with towering structures, pipelines, and flames that never go out. This is where transformation begins. The first major step in processing crude oil is called fractional distillation. Crude oil is heated to extremely high temperatures until it turns into vapor. That vapor then rises into a tall distillation column. Inside the column, temperature gradually decreases from bottom to top, and something remarkable happens. Each component separates based on its boiling point. Light gases rise to the very top of the column. Gasoline forms in the middle section, while diesel settles lower down. Heavy residues remain at the very bottom. From a single raw substance, multiple valuable products emerge. But there's a problem. The amount of gasoline naturally produced is not enough to meet global demand. So scientists developed a solution: cracking. In this process, large, heavy hydrocarbon molecules are broken into smaller ones. This controlled transformation creates more gasoline from heavier fractions. It's not just refining anymore, it's redesigning matter itself.
Want to see something crazy? Holy shit. God.
Now we have gasoline, but it's still not perfect. For engines to run efficiently, fuel must burn in a controlled, stable way. This depends on something called the octane rating. In the reforming process, molecular structures are rearranged to improve performance. The result: smoother combustion, more power, less engine damage, purification, removing hidden dangers. Crude oil contains harmful elements, especially sulfur. If not removed, it can damage engines and cause serious environmental pollution. So the fuel undergoes deep purification. Invisible impurities are stripped away, leaving behind a cleaner, more efficient product. Sulfur, chemical symbol S, is a fascinating naturally occurring chemical element. It's a non-metal element, typically yellow, found in various forms throughout nature. Its most recognizable property is its distinct bright yellow color. Pure sulfur has no smell. However, its compounds often produce a strong, characteristic rotten egg odor. At room temperature, sulfur exists as a stable solid. It's also a flammable element capable of burning with a blue flame. So where exactly can we find this versatile element? Sulfur is present in crude oil and natural gas deposits deep beneath the Earth's surface. You can also discover it in volcanic rocks and around active volcanic vents. It's an essential component found in soil, contributing to plant health. Remarkably, sulfur is even found within the human body as a vital part of some proteins. Why is sulfur's presence in gasoline such a critical concern? If sulfur remains in gasoline, it significantly contributes to air pollution. High sulfur content can also cause severe damage to car engines over time. Furthermore, burning sulfur-containing fuels produces harmful and toxic gases. That's why refineries employ a process called desulfurization to remove it from fuel. The infamous rotten egg smell is actually hydrogen sulfide gas, a compound derived from sulfur. Now comes the final step, blending. Different components are carefully mixed in precise ratios. Additives are introduced to enhance performance. Engine cleaning agents, antifreeze compounds, efficiency boosters. These formulas are often closely guarded secrets, developed by major energy companies. And now, this clear, powerful liquid is ready to fuel the world, from ancient oceans to modern highways, from microscopic life to global energy systems. Every time you start your car, you're using energy that took millions of years to create. Gasoline is not just fuel, it is time itself, compressed, refined, and released in an instant. Gasoline is not just fuel. Refineries add special additives to protect the engine and improve performance. Detergents keep fuel injectors and valves clean, preventing carbon buildup. This results in better combustion and lower fuel consumption. Octane boosters increase resistance to engine knocking and help fuel burn more smoothly. This leads to smoother engine performance and less damage. Corrosion inhibitors protect metal parts in the fuel system, preventing rust and corrosion. This ensures a longer life for fuel pumps and pipes. Water control additives prevent water buildup in the fuel tank, helping separate or neutralize moisture. This results in better engine starting, especially in cold weather. Cold flow improvers improve fuel performance in low temperatures, preventing starting problems in winter. Fuel system cleaners clean fuel lines and remove deposits, working alongside detergents for deeper cleaning. Stabilizers prevent fuel from degrading over time, maintaining fuel quality during storage. Without these additives, engines get dirty, fuel consumption increases, and parts wear out faster. With these additives, the engine runs cleaner, smoother, and lasts longer,